Everybody, thank you for coming today to our FLL coding camp. We're the Future Martians, FRC Team 9023. Last year, we competed in our second year of FIRST Robotics competition, and we learned a lot of cool things about engineering, tech skills, and programming, and a lot more than that too. We made it all the way to the World Championships in Houston, Texas, and ended up as quarterfinalists in our division. Most of the students on the team have experience with other FIRST programs like FLL and FTC, and we have worked our way up to FRC as Team Future Martians. Do you guys want to start introducing yourselves?
Hi, I'm Shreyan. Villain, we can see you.
Okay. Maybe we can go over like what school we go to and what grade we're on.
So me and we go to Cascade Ridge. This is our second year of FLL. Yeah.
What team are you guys on?
We are Tech Titans. And I forgot.
All right.
Yeah, we're team 6177.
All right. Do you want to introduce yourself?
I don't remember the name of our team. My name is Zoe.
Nice.
Yeah. What are your guys' names?
My name is Nohida.
I'm part of Team 028. My name is Sahasra. I'm also part of 6230A.
Nice. All right. Does anybody else want to introduce themselves that hasn't already? Okay. We can move on then.
Sorry, it's actually 6023A.
Okay. All right. Now we're going to move on to the Spike Prime hardware overview, which Lucas is going to talk about.
All right. So first thing is the Spike Prime brick. So the brick is basically the robot's brains and it's controlling all the motors and the sensors connected to it. The brick has a 5x5 customizable light matrix, a speaker, and stores up to 20 programs. The brick has 6 inputs and output ports, along with a built-in gyro sensor as well. And the brick has Bluetooth and micro USB connection options as well.
So just a few quick questions to all of you. So all of you have had at least one season of FLL, correct? So everyone who's on Zoom, you've all had one season of FLL, is that right? At least? Okay.
Yeah.
So that means you probably know all of this and you have ways in which you store your programs and you know how you're going to run them when you are in the competition, when you have different mission runs. So as we go through this, if there are questions you have regarding things like that, please feel free to go ahead and ask. The team members will be happy to answer any of those kind of questions.
Yeah, feel free to unmute or just put them in chat. It's up to you. All right, we'll move on to the next section.
All right, so for the motors that we use for the Spike Prime, we mostly use 2 types of motors, the medium and the large. The medium motors are for lighter loads. They have a higher max speed than the larger motors and are very compact. To use them as drive motors, you need a lighter robot. The large motors are for high power, high torque applications, but are larger and slower than medium motors. They would make better drive motors for heavy robots. What did you guys use for your robot last year? The medium ones or the? Yeah.
We use both.
All right, what about you guys?
We're just using the big motors for here because they can basically train
All right, anyone else on Zoom?
So this is excellent to hear. That means what we just heard here is teams have used different combinations, and that's exactly what is being communicated here. There is no right or wrong answer to using large or compact motors for drive. It really depends on how your robot is designed, how heavy your robot is, and when you have attachments which are going to do the work for you, how much power you need in those attachments. Do you need the attachments to be faster, or do you need them to be able to carry heavier loads? So that's excellent to hear that there's a combination of this being used already.
Hi, so another important aspect of Spike Prime is the sensors. So there's a lot of sensors. Let's first cover the basic ones. So there's distance sensors, which detect how far away an object in front of it is. They have like a max range of 200 centimeters. There's also force sensors that detect the amount of force being acted upon them, and they detect up to 10 newtons. But they can also be used as touch sensors. Color sensors measure reflected light, along with being able to distinguish between 8 different colors. There are rotation sensors inside the motors, and there's also a built-in gyro sensor built into the brain of the robot, which we'll cover next.
So I guess we didn't introduce the speakers. So this is Ranga,
Oh.
who just spoke about the sensors, and Naman, who just spoke about the motors, and Lucas spoke about the brick, and he was our president last year, our team's president. Okay. So yeah, you guys can go ahead and introduce yourselves if you haven't already.
My name's Aditi. I did the introduction. But the next sensor is the gyro sensor. So as Ranga talked about, the brick has an inbuilt gyro sensor that has a 3-axis gyroscope and a 3-axis accelerometer. The gyro can measure the pitch, roll, and yaw angle of the spiked prime brick, and can also determine its orientation. So if you just look at this picture here, the yaw is which way the robot is facing, like this. The pitch is which way it's facing, like this, like up and down. And then the roll is its rotation. And the accelerometer also allows gestures to be detected. So if you want to like maybe do something like start a program by tapping the brick, you could do that. Or if you want to shake it, you can also do that. Next, we'll move on to the programming section.
So before that, let's just ask them about the sensors they've used. So you've all had one season, or you have some experience programming FLL robots. So we're just wondering, what kind of sensors did you all use in your first year? So we'll actually go one by one and ask. So we'll start in person first. Yeah, you can go ahead.
Anyways, we have 2 color sensors at the front wheels, and as you can see, there's like a rack for slip-on attachments. So, whatever color the attachment is, it plays a specific part of the code, for a mission.
Okay, that's good. And you use this mechanism in your competition?
No, we actually were. We didn't use any color sensors. We had them at the bottom for last year, but they really didn't do much for the sense for us. So we just moved them up for the.
So executing program. That's a creative way of starting a specific program. That's awesome. Okay, thanks. So who wants to go next? Do you want to talk about it?
Sensors, mainly because we didn't have a use to use color sensors. Because during the masterpiece, it was kind of hard because the robot would kind of like shift itself as it moved along the black and white lines. So just not as efficient, it's just moving straight ahead. And then the touch sensors, there wasn't as much need for that, because they just translate like how much we need to move. Even the distance sensors.
Okay, all right. And that's good to hear. And as you can all see, this is the map for submerged. And as you can see, there aren't too many lines to follow here. So color sensors will probably not play as big a role in line following, because it won't get you from your home areas to your mission models. So, which is why I think the gyro sensor and PID going straight and furnace will not be with their role this year. I think you were trying to say something about. Okay. And one more sensor I'm sure all of you end up using, which we forget is a sensor, is the motor's rotation sensor, right? So you're always keeping track of how much the motor is rotating, and that is also a sensor that's inbuilt in the motors. So now let's move on and ask the members who are attending online. So if you guys want to share one by one about what kind of sensors you use and what was your experience and what you're looking to do this year, that would be great. Milan, do you want to start us off?
Okay, so in last year, our color sensors didn't really work that well, like Shreyan said. But this year we're probably gonna take them out and exchange them for something else.
Okay. Anyone else want to share their experiences on what sensors they've used and what their experience was? Okay, so has anyone used the gyro sensor last year?
We have,
Okay.
I think.
Okay, all right. And so we have an attendee here who has used it. Did you want to say something about how you use it, what your experience was?
So the gyro sensor is honestly really helpful because you can tell like how much you're turning and just regulating. A lot better than like when we use just like calculating how much you have to turn. You just have like wait until and then it stops.
Exactly.
Okay, now I remember we did use it. It was like, wait until, position is, so, stuff.
Right, okay, yeah. So the gyro sensor, as we learn more details, is going to be really helpful in more accurate behavior. And one thing we always start, when we mentor FLL teams, one thing we always make very clear is the difference between accuracy and precision and how important it is. So accuracy is about getting it right, but precision is about getting it right every time. Because I'm sure you've all had experiences where a program ran, you were so happy that the mission was executed. But then when you go back and run it after a few days, you say, well, that was not working anymore, right? And that's where the precision level is low. And using gyro sensor, using the PID algorithm and mechanisms like that will help you overcome the reason. And that's what's going to be largely covered here in today's talk. So with that, Aditi, you want to make sure they understand what is yaw?
Yeah. So
Let's realize that because I yeah.
So the yaw is which way the robot is facing. So it's usually left or right. So if you guys can see my hands, it's like this. So which way you're facing. And then pitch is when you go up and down. So if you think of a plane when it's taking off, when you angle upward and downward, that's the pitch. And then roll is also like a plane when you angle yourself like this, that's the roll. If you're like rolling the robot, that's why it's called roll. Does that make sense to everybody? Okay.
So for turning.
Usually you guys are going to be using yaw. So yeah.
And one more thing to add there is maybe depending on your robot design, you might mount your brick at a different angle and not exactly as shown in the image there. And when you do that, please remember, maybe yaw won't work. And depending on how you mounted it, you may have to use the roll or the pitch to figure out when you're making turns. So this is something to keep in mind when you design your robot, and the coding team needs to be made aware of the fact that they will need to do this differently. Of course, you all do everything, so there's no separate coding team. So each of you has to be aware of the implication or what happens if you mount the brick differently from what is shown on the slide.
Okay, now we'll move on to the programming section.
I'm Isha, and I'll just go over the basic programming stuff. So motor blocks are blocks concerning movement of individual motors. Movement blocks are blocks concerning movement of drive motors. And light blocks are blocks that control the light grid. Sound blocks are blocks that can control the speaker. Events are when blocks and broadcasting. Control blocks are wait blocks, conditionals, and loops. Sensors are blocks concerning reading data from the sensors. Operators are mathematical blocks. Variables are blocks for using created variables, and my blocks are blocks for creating and using my blocks. So these are motor blocks, and as you can see, there's start motor blocks, stop motor blocks, and set speed to certain percentage motor blocks. And then these are movement blocks. So yeah, stop moving, start moving, which direction to move, that. These are light blocks, and they like tell you what you want to put on the pixels on your brick. So there's turn off pixels, there's pixel brightness, and yeah.
So when we start working on the code, we'll definitely do that. But yeah, this one was more to illustrate how
Yeah.
all these.
It's more about these blocks. Not those ones. Okay, wait. I don't think so.
So yeah, it's like you can only zoom in the actual code now.
If you guys want to open spec part of your laptop, so you can see the different sections.
Yeah. Definitely. Okay, so if you can switch back to the slide, I just wanted to talk about a couple of things. So as you may have all realized, the motors blocks, those are useful when you're probably working with the motors that work on their attachments, because you're controlling individual motors using the motors blocks. You could use those to control the drive motors too, but it is better that you use the movement blocks, because right in the beginning of the program, you're going to pair up two of the motors and call them as your drive motors. And then you'll be able to use the movement blocks to work on both those motors simultaneously. So that's definitely the way you should be working with any movement of your robot around the FLL map. And then light and sound, depending on whether you're using something that requires it, that's probably one of the lesser used set of blocks. And then events, this is really important because when something occurs and you want that to trigger something else, you need those event blocks. And then control blocks are important because when you're making decisions, and these decisions would be based on something else happening. So the reason all these blocks are really important is, as you will see, when you go through the gyro-based turning, T-control turning, as well as PID-based going state, you will be using a combination of all these, the events, the control, and then sensors also, because any data that you get from the sensors, you will be using as input for what you want to do through the control blocks. And operators and variables. So these are interesting blocks as well, which you need because they will hold information for you in your program, and you'll be using that. And you'll be using the operators to manipulate that information and keep adding to a variable. How many of you have not used operators and variables? And please remember, there's no right or wrong answer here. We want to make sure that everyone is comfortable with what they're learning and has the best that can come out of this camp. So let us know if, let me get all the other videos to show up. So if anyone's not used operators and variables before, please do let us know. And then lastly, my blocks, as you've seen, if you've used my blocks, it just makes it easier to reuse pieces of code. Because as you're going to see, they're going to show you how to go straight reliably. And you want to use that every time you have to go straight in your program. But you don't want to be writing your code for that whole complex piece of code again and again. You want to reuse it after defining it once. That's where my blocks is going to help you. Okay, so with that, I think the next slide, we're going to talk about extensions. Yeah. Thank you.
All right. So to make sure that you have all the blocks you need to make your code reliable, you have to make sure you have all the correct extensions added. So everybody open up Spike Prime on your laptop and make sure you have the more motors and more movement extensions. So first, click on this button right here. Does everybody have Spike Prime open? All right. So click on,
And from online, so.
okay, does everybody online have Spike Prime open? Okay. So make sure you click this button right here. It's at the bottom of your screen next to all the categories of blocks. And then once you click that, you should get this screen open. And make sure you have the top two on the right-hand side selected.
So please give us a thumbs up if you are now at the screen, the extension screen, which shows you more motors and more movement.
And let us know if you need any help getting that open.
Yeah, we'll wait for everyone to give a thumbs up. So Nikhil, Sahasra, Avita, and if you can scroll down. Yeah, Alex and Elijah, if you can all please give a thumbs up once you're at that screen.
All right.
Okay, perfect.
So having these extensions added will make sure you get all the blocks you need to do the code in the later programs.
So do they just have to click on that?
Yeah.
And that will install it for
Yeah.
them? Okay.
Make sure you have the check on both of them.
So if they don't have the check, they just have to check on it, right?
Yeah.
So yeah, please go ahead and if you don't already have those two checked, click on it so that it gets checked, and that will install them or make it available to you immediately.
Okay, now we'll move on to gyro turns.
Yeah. So please give a thumbs up if you all have that available now. If you don't, we'll just wait. So let's see. Yeah, so we're just waiting till everyone has both the more motors and more movement sections or extensions checked. Again, some of you may have already had this, and that's totally fine, but we just want to make sure that going forward you have it, because you will need those extra blocks for the code that you start developing here shortly.
You guys can put in the chat if you have it, right here, you have it, the extensions added.
So give us a thumbs up if you have the extensions checked. Otherwise, if you're having an issue, please send a message in chat and we can talk about it. Or you can unmute and talk to us. Oh, wait, I think they after giving a thumbs up, they took it
Yeah,
away. I
it
think
goes
they're just saying because they've already done it. So if you all don't mind, if you can leave your thumbs up on till everyone. Oh, the auto takes it away. Oh, let's see. Okay, looks like everyone already gave us a thumbs up. Okay. Okay, we'll move on to the next slide.
Right, okay. Cool. All right. Hello, I'm Sashmit and we're gonna go presents. Okay. Okay. So we're gonna be talking next about turning with the gyro sensor. So let's begin with this basic gyro turn. So it's a basic turn that uses the gyro sensor. And we're doing it in a my block. So as we said earlier, we're doing this because it makes this block of code easy to use. So if you define the code for turning, then you can use this my block anytime you need to turn. So it's quite useful. So basic things like turning, going forward, and even some functions for your attachment motors would be useful to place in a my block like this. So this my block here has an input of target angle, which determines how much the robot needs to turn in degrees. So we begin by setting the yaw angle to 0. And then we set the movement motors. So for the demonstration robot that we have, the movement motors are A and E, but for your robots that may be different. We also set the movement motors to brake at stop. So what that means is when we stop the motors, instead of just cutting power to the motors and allowing the wheels to coast to a stop, we make sure that they brake at stop. So we make the motors apply power to actually stop the wheels. And then we set movement acceleration to smooth. So this is to improve accuracy, to ensure that we're not suddenly starting or stopping the robot. So the 2 blocks here set movement motors to brake at stop and set movement acceleration to smooth. You will find in the more movement extension, which you should have just added to your spike prime. Yes. Oh, sorry.
So if you get acceleration smooth, it says medium slow.
Oh, do you have the latest version of Spike Prime? Oh, okay. Okay. It does, okay. Then you can just use medium. Okay, if you have the option for smooth, then use that. Otherwise, medium should be fine. Okay, yeah. Thank you for asking that.
Where is define basic gyro turn, right?
Yeah, how do you switch the, okay. Okay, so here's how you do it. Can we see the Spike Prime? Okay.
So yeah, just requesting everyone, you will all be implementing this code. So you can go ahead and open up your Spike Prime and we're going to expand this so that you can see the code more easily.
Yes.
Please let us know if it is easier to read this now. And for the movement motors, the block where it says set movement motors to, please make sure that you pick the 2 ports that you have your movement motors connected to. And is it left and then right?
For the
A plus E rather than E plus A?
it's right and then left. Oh yeah,
Right.
that's a good point.
Okay.
Yeah, so yeah, as I just said, the movement motors here, if you're not familiar with that, it's the right motor first and then the left motor. Okay. So for your question about how to get this definition block for the my block. So over here on the sidebar, you have to go to the my blocks section and then click here, make a block. And then you can,
Go ahead and fill the same program.
Okay.
For them,
yeah, sure.
as you explained.
Okay,
Each thing is one.
yeah, sure. Okay, I should be able to just do it here. Okay. All right, so yeah. So go to the my blocks section on the sidebar and then click here, make a block. Okay. Is everyone here?
And everyone, feel free to unmute and talk or ask question or ask us to wait. All that's totally fine. Or if you want to send a message in chat, that is fine too.
Oh, do we have to copy the code?
Yes, so well, what we're asking you is to, so I'm gonna actually code that my block with you guys right now. So what we're asking you guys to do is to actually code it along with us so that you can then test this code on your own robots. Does that make sense?
It does.
Okay. Okay, so if everyone is at this screen, if you've clicked make a block, then you can name your block. So for this one, it's the basic gyro turn right. And this is a basic turn. It's not the most accurate, but it's just to get used to how the gyro sensor works. So this is probably not the one that you guys should be, I mean, this is not the way that you guys should be using how to turn in competitions. It's just to get used to how the gyro sensor works. Okay, so once you have the my block named, then you click here, add an input, number, or text. So as I mentioned on the slide, the input that we need to be giving to this turn block is the target angle in degrees. So it's a number input, and we just name it target angle. Okay, and that's the only input we should need. So once you have this, you can just click save. And then somewhere in your workspace, you should see this definition block pop up, and the whole code for the my block will be defined under this. Okay, did everyone get this my block definition block?
Yeah,
Oh, no, that's
pretty
yeah.
much.
Okay.
And just want to stress again, like Sashwat indicated, this one you're doing, you're putting this code together just so you have a gyro-based turn. In competition, we do not suggest you use this. After this, you'll be writing another program, and that's the one we suggest, or similar to that is what we suggest you use during competition. Now, is there anyone here who does not have Spike Prime available to test their code on today, like during the camp? We just want to know so that we make sure that you get a chance to watch us doing this on our robot here. If you do not have a robot available, a Spike Prime robot available for the camp right now, please give a thumbs up so that we know.
Oh, the people at the camp.
Yeah, the people at the
Oh.
camp. Oh, right. Oh, yeah. So,
Okay.
so that means Nikhil, Milan. Yeah. So, yeah, there are three brothers, I think.
Okay.
Yeah. So that means you will have access to this later on because, your robots here, your other team members are going to run the code on there, but once it's back home with you guys, you can test the same code, and we are available to help out if need be. Okay. All right. So let's continue.
Okay, so if everyone has this, then we'll start coding the my block. So okay. All right, so what we're gonna first do is set the yaw angle to 0, set the movement motors, set them to brake at stop, and then set the acceleration to medium, or if you have it, then you can use smooth.
Actually, I want to indicate the importance of why we're lying.
Yes. So yeah, the reason we need to set the yaw angle to 0 is so that our turn, because if the yaw angle of your robot is not 0 when you begin the turn, what's going to happen is that your robot is only going to turn until the gyro sensor reads what your target angle is. So say you wanted to turn 90 degrees, but your yaw angle before the turn was already 45 degrees. So instead of your robot turning 90 degrees from where it is, it's only going to turn 45 degrees to reach the absolute angle of 90 degrees. So it's important that we reset the yaw angle before we do any turn so that our robot turns the exact amount which we need it to relative to where it starts the turn, not relative to where your robot has begun its program.
So is this clear to everyone? Because this is a really important factor as we use the gyro sensor. You want to set it to 0 before you.
Okay. Does anyone have any questions about the first 4 blocks in this my block, or are we good to start encoding this? Okay, cool. Oh, wrong way. Okay. Okay, so like I said, the first thing we need to do is to set the yaw angle to 0. So we'll put that here. Oh, sure. 1 second. We'll do this. Oh, okay, okay.
Top right, it's
Yeah.
connected already.
Is it green?
Yes.
Okay. There we go. Cool. Okay. So now we're gonna set our movement motors, and if you want to do this outside of the my block in your start when program starts stack, and that's probably what you, I mean, if you have multiple blocks and it's an actual mission run, then that's probably what you should be doing, because you need to be setting the movement motors for all of the movements, going straight, turning everything. You need to be setting your movement motors to use any of these movement blocks here. But since we're not since this is the only block we're going to be running now, we'll set the movement motors to A and E. And then in the more movement section, which you should have just added, you'll see these 2 blocks. So set movement motors to brake at stop, and then set movement acceleration to medium. And these 4 blocks you'll see everywhere. So in all of the my blocks we're going to be doing, these 4 blocks will be there. These are boilerplate blocks, so they should be done at the beginning of every movement so that you have the accuracy as well as the proper motors, and of course resetting your yaw angle every time you turn. Okay, does everyone have these in the my block? Yes. Okay. Everyone online as well?
Yeah.
Okay. Looks like that's everyone. Okay. Nice. Okay. So now let's talk about what these next blocks are. So we need to start the wheels moving to turn the robot to the right. So this block will only work to turn the robot right. So to turn the robot right, we need to make the left wheel move forward and the right wheel move backward. Does that make sense to everyone? Has everyone heard of that? Yes? Okay. Okay, so we need to make the left wheel move forward and the right wheel move backward, and then we continue moving until the robot reaches 5 degrees before the target angle, and then we stop moving. And the reason we do this is to allow for the overshoot, because we are suddenly stopping our robot. So there's a lot of built up momentum from the turn, and the robot is going to overshoot a bit after the motors stop. So that's why we account for this 5 degrees of overshoot. Now, one thing to note is that the exact amount of overshoot that you can expect is different for each robot. So it depends on the speed that you're turning your robot at, as well as the weight and other specs of your robot. So for the robot that we're testing this on, 5 degrees is about the amount that we can expect it to overshoot. But for each robot, that's going to be different. And again, this is why this turn is not, the best option for you guys to be using in actual competitions, because it doesn't have a smooth deceleration, which is why we have this overshoot. Okay. So does anyone have any
So,
questions?
One quick request. I know you're all eager to get that code up and written up. What I would suggest is work with Sashnet here, listen to whatever he's saying as you add each block one by one. Because putting the code together, I'm sure you're all really quick at that. What he's saying explains each block, and that's valuable knowledge for you all to gain. So please do it one by one along with Sashnet, rather than trying to get the whole program written up very quickly.
Okay, so are there any questions, or else we can start adding these blocks? Okay, looks good. So the first thing we need to do is to make a variable called target angle. And this is just to make our code easier to understand. So okay, cool. So let's create a new variable called target angle, and you can do that by just clicking make a variable in the variables section, and then make a variable called target angle. And then we want to set target angle to this input target angle -5. And again, that's to account for the overshoot. That's why we're stopping our robot 5 degrees earlier. So set target angle to target angle the input -5. And then we need to start our wheels moving. So in the more movement section, drag out this block, start moving at 50% speed. And what this does is you can specify the speed of each wheel individually. So we need to do 20 and -20, right? Is that what it says? Yes, 20, -20. Okay. And then after that, we need to wait until we reach the target angle. So wait until here. Okay, wait until yaw angle is greater than target angle. So we need to wait until we've passed this point, which is 5 degrees before the target angle. And then, where did we go? Here. Yaw angle. And then after we've passed this point, we need to stop the motors, which is in the normal movement section. Stop moving. Okay. And this should be it. So if you guys want to test your code, is there an issue? Okay. This should be it. I'm just gonna check it with what we have here.
Sash, maybe go ahead and show them how to use the my block.
Yes. Okay. This looks good. And so yes, now let's actually use the my block. So for that, we need to go to our second. Whoa. Okay, here, the when program starts. So I'm gonna take this away, zoom back in. Okay, so for anyone who is wondering how to use the my block. Oh, yes. Okay, 1 second. All right, yeah, we're good. Okay, so for anyone that is wondering how to use the my block, you need to go to the my blocks section on the sidebar here, and then drag out this basic gyro turn right, which is the block we just created. And then for the input, put whatever angle you want to turn to. So say you want to turn 90 degrees, just put that in here. And this is the block to make your robot turn 90 degrees to the right. Okay, are there any questions about this my block and what we just coded? Okay. So if everyone has this and understands it, then you can test it on your Spike Prime robots if you guys have them at home.
Another way you can check how much you rotated already is by clicking here, and you can see the yaw value that you've already gone. So you can check how accurate you are.
Cool.
Wait, oh, I think it is.
Is it working for us? Is it working for everyone at home?
So yeah, if you've all had the mat available, I mean the robot available, you can run it either on the ground or on a mat. and see if you're able to turn 90 degrees, right? You want to run this please?
Sure. Oh, on that robot, sure, we can. Okay,
So Ron, that should be.
is that our robot? There we go.
Okay.
Cool. Yeah, and if you guys are wondering how to turn left instead of right, the next block that we're gonna create is one that will work for both left and right turns. Like I said earlier, this block is mainly just to get you guys used to how my blocks and the yaw angle work. But the next one we're gonna be doing will work for both right and left turns. Oh. Okay. And if the robot you have weighs more, if it's a bit bigger, then the overshoot will probably be more than 5 degrees. So just take that into account. If your robot is consistently overshooting, that probably means either you've set it at a higher speed or it's heavier, which is fine. You can just increase this amount from 5 to whatever your overshoot is.
So the question here was, you know how we have 5 or 10 for the overshoot?
Right.
So he was asking about the values because, so there's 47.
Yeah, so it's 47 because starting it was at 100 and negative 100.
Right.
So it's really high.
Yeah, so I made 47.
So as you'll see, so this one again is a basic turn, right, which we are not really asking you to use in competition. So the next one you'll see, based on the amount of degrees you want to turn, the power will be according to that. So that will take care of this concern.
Okay, yeah. The next block we're gonna use will also work for both right and left turns. So for anyone wondering how to do a left turn, we'll be able to do that with the next block. Okay, did this work for everyone that could test it?
So whoever's on Zoom, if you had a chance to test it and if it worked, please give us a thumbs up.
Yeah, and if you've had any errors, please let us know. We can help you solve them.
You can use chat or you can unmute and talk if you are having any issues, if it didn't work as you expected.
Everyone's good? Okay. We're good.
So I'm trying to get some of the so it's like
After the time.
yeah, but I change it.
Did it?
And what speed was it?
The speeds were showing.
So that would explain, you know, how did overshoot by you degrees?
No, I didn't overshoot. Targeting was set.
Okay. How much is this amount here targeting?
Yeah, 47.
Oh, okay. Oh, okay, that, okay. All
So
right.
The target angle minus 47, I think as you make it smaller. it should be okay. But anyway, all that will be taken care of in the next step, because it won't be. That's actually using competition.
Yes, okay. So if everyone is good with that, we're gonna move on to this turn. It's the P control turn. And this is the one, like we said, that we suggest you use in competitions because it's more accurate and it's something that's gonna work consistently. Okay, so first let's talk about what P control is. So the P control or decelerating turn uses the gyro sensor to slow the robot's turning speed as the error reduces by using a proportional algorithm. So what this means is essentially as the robot reaches its target angle, it's gonna slow down. So that's the decelerating turn. And the proportional algorithm that we're going to use is that speed is proportional to error. So before we move any further, I just want to make sure everyone knows what a proportional relationship is. Yes,
I
any
want to
questions?
request everyone to pay attention because this is an important thing that will carry on into some of the upcoming code and also the PID algorithm. So please pay attention. I know you're all eager to get some code working. And that's why we keep requesting, if you want more time to finish some code that you're working on currently, let us know because we want you to finish that and then pay full attention to this part.
Okay. So everyone is comfortable with using proportional relationships? Yes, good. That's great. Okay, so let's talk about what is error. So error is how many degrees away from the target angle the robot is. So it's essentially how much more the robot has to go to reach its target angle. So the way we calculate error is target angle minus current angle. So the target angle is the input we get from the my block, and the current angle is just the robot's current yaw angle.
So let's ask a question at this point. When you start your program, what is the error at that point? What is the error angle when you are just starting your program?
We haven't moved at all, and we want to go a certain. Wait, how much do you have to go left? Yes.
Right,
That is the error, exactly.
right,
So the target angle is the error angle when you're starting. And as you turn, that error angle is going to keep reducing. And as that is reducing, so does the speed of your turning. That's how you're much more accurate, because remember how earlier on, in fact, maybe you want to explain this, how earlier on, there's one check, whereas here,
Right.
there's a check for everything.
yeah, yeah. So with the previous block, we only have one place where we check what the yaw angle is, and that is this wait until yaw angle is greater than target angle. So we're only checking once what the yaw angle is, and there's only two states of the motors. Either you're moving at this full speed or your motors is stopped. There is no smooth deceleration. It's just full speed or no speed. And there's just one check that determines whether your robot is moving or whether it's stopped. And the problem with this is you are suddenly stopping the robot. There's no smooth deceleration. And that is why we have overshoot. So that 5 degrees there, right? It's the overshoot because of the built up momentum. When the robot is suddenly stopping, you have all of this built up momentum, and that causes the robot to skid past its intended target angle. So where the motors have stopped, your robot actually moves past that. And that is why we get the overshoot, which is the reason that we stop the robot 5 degrees before its actual intended target angle.
There's two types of like errors you can get when starting and stopping a turn. It's called slip and skid. So what Seshma just talked about is skid. What skid means is if you ever get on like an icy road and you hit the brakes, but you keep on moving, but your wheels aren't rotating, that's skid, so you're skidding across. So if you stop a turn too quickly, you're gonna keep skidding and move even though you don't want to. And then slip is when you start a turn, so when your wheels are rolling, like your wheels are moving, but your robot isn't going forward because your wheels are slipping on the road. Does that make sense?
Yeah.
So by using a decelerating turn, you're reducing the amount of skid that you have.
Right. Yeah, so it's essentially like if you guys have ever run down a hill super quickly, you can't stop immediately after, the hill is over, right? It takes you some distance to actually reduce your speed. So that's the same problem we're having here. That's why we have to account for this overshoot. But if we're smoothly decelerating, then we don't have all of this built up momentum when the robot is trying to stop. So we don't have as much overshoot. Okay. So as we said earlier, at the beginning of the turn, before we start moving, we set the error to the target angle because the robot has not moved yet. So it's this essentially this formula, target angle minus current angle. But because the current angle is 0, the error is just the target angle, how much you have to move. Okay, are there any questions at this point? No? Okay, so let's code then up to there. So to do this, we're gonna need to define a new my block, and we can call this p con.
Maybe they
Yes.
modify.
Oh, right, yeah,
Question,
yes.
do you make a new page for this or do you do it in the same page?
That's your choice. I'm gonna be doing it in the same page because you can have as many my blocks as you want in the same page. But if you prefer to make a new page, that's completely fine.
Copy of that. Start modifying the top.
Well, you can't copy into my block. Yeah,
Oh, okay.
yeah, that doesn't work. Okay, so I'm gonna continue on with making a new my block in the same program. So I'm gonna name it p control gyro turn. And then just like the previous one, we're gonna need one number input. So click this add an input number or text, and we're gonna call it target angle, just like with the previous block. And then click save, and then you should see the definition block. There, okay. Definition block pop up right there. So I'm gonna move this block out of the screen, and we're gonna use this. Okay, so just like with the previous block, there's these boilerplate blocks which you want to have at the beginning of every one of your movement blocks. So that's the, first of all, set yaw angle to 0, and then set movement motors. It's B. Okay, that should be E. No. Okay, set movement motors, and then we need to set movement motors to brake at stop, and then set movement acceleration to medium. Okay. Once this is done, we need to set our initial error, which is just the same as the target angle. So we already have something called error. Okay, so we already have a variable called error, so I'm just going to use that. Set error to target angle before we start moving. Okay, so does everyone have these 5 blocks here on the my block? Yes?
No,
No, okay, I'll wait.
I'm not ready.
Okay, that's completely fine. Take your time. Okay, yeah, just let us know when you guys are ready to move on, and we can move on.
Do we make a variable called error?
Yes,
Is-
so yeah. So you should be making a variable called error.
Okay, I thought it was in the control area for a sec.
Oh, no. Yeah, it's a variable. Yeah, those colors are a bit similar. Yep,
I'm done.
you're done? Okay. Is everyone else also done? Okay. Are we good to move on?
Okay.
Yes, ready.
Okay, cool. So we're here. Okay. So now we have this loop, and basically all the blocks that are inside this repeat until loop, those are the blocks which we're going to use to actually move the robot and get it to turn. So the first thing we need to do is to recalculate the error, because every time this loop runs, our error will keep getting smaller and smaller. So we use this formula up here, error equals target angle minus current angle, to keep calculating our error. And then we need to use the proportional algorithm to calculate speed from the error. So we need to do speed equals the proportionality constant times the error. So in our example, 0.5 is used as the proportionality constant, but this constant needs to be specifically tuned for each individual robot. So it depends on things like your robot's size, your robot's weight, and even which motors you're using for your drive wheels. So for us, 0.5 is what works well, but for each individual robot, that could be a bit different.
Like what is the content is because you know what you robot turn at full speed, you can multiply it by something less than one to make it a little bit slower.
Right. And as long as we're just multiplying the values, they'll still be proportional. Okay. There's a question in the chat. That looks like. Yep. Don't worry. Okay. So does everyone understand the proportional algorithm, how we calculate speed?
I do.
You do? Okay. Everyone in person? It's here. Yeah. Oh, I can zoom in. Okay. It's here. We're not coding this yet as of now. I'm just explaining it, but it's this set speed to error times 0.5. Okay. Right. And okay. So next we have to do something called a lower bound clamp. And the reason why we do this is because the motors will not run at a speed lower than about 5. So if the speed is lower than 5, we need to set the speed to 5, or the same thing if it's a negative speed, because if we have a speed lower than that, the motors will not run. So if the speed is between 0 and 5, we set the speed to 5. And if the speed is between 0 and -5, then we set the speed to -5. And we need these two separate checks, because if the speed is positive, we need to keep the speed positive. And if the speed is negative, we need to keep the speed negative. So as it says down here at the bottom of the slide, if the error and speed are positive, the robot will turn right. And if they are negative, the robot will turn left. So it's important that if the speed is negative, we keep it negative. And if it's positive, that we keep it positive.
The reason why is if it's less than 5, if the speed is less than 5, then it might not be enough power to actually start the wheels, and then you'll be stuck there to not exit the program.
Okay, there's one question in the chat from Mohita. So how did you set the movement acceleration to smooth? If you don't have that option, just go ahead and set it to medium. That should work just fine. Okay. So we're all good with the lower bound clamp. Then let's move on. So we have the calculated speed, and then we clamp the speed with the lower bound of 5. And then we set the motors to move at the calculated speed. And that's that here. So start moving at speed, and speed times -1. And the reason we do this is just because if we want to turn, one motor has to move one way, the other motor has to move the other way. that's why one is positive and the other wheel speed is negative. And then once the robot's heading is within 2 degrees of the target angle, the robot stops moving. So this number 2 degrees is called the is the tolerance. And what that essentially means is that we allow the robot to have an error of 2 degrees either way. So it can undershoot by 2 degrees or it can overshoot by 2 degrees or anything in between. So for example, if our target angle was 90 degrees, this tolerance of 2 degrees would allow the robot to stop moving anywhere between 88 degrees, 2 degrees before 90 degrees, or 92 degrees, which is 2 degrees after. So we have this range of tolerance. And the reason we do this is because if we didn't have the range of tolerance and we said that the robot has to turn exactly 90 degrees, then we would have a problem of hunting. So the robot would have to hunt for the exact target angle. What that means is it would constantly go back and forth in super small amounts until it reached the exact angle of 90 degrees. So it's going to turn and then it's going to keep moving forward or back and forth, trying to search for the exact angle. And that wastes time and we don't want to do that. So often having a tolerance of something small like 1 or 2 degrees is fine. It saves a lot of time because your robot will not spend time hunting for the exact angle, but most of the time it's accurate enough that we can allow this much error. And the reason we use absolute value of error is because error can be either positive or negative, right? If it's positive, we're turning right, and if it's negative, we're turning left, as I said. So because we have the possibility for error to be negative, we need to use the absolute value, so it works for both left and right turns. Okay, so does anyone have any questions about the movement loop? Online? We're good in person? Okay. All right. If there are no questions, then we can begin adding this to our code. So the first thing we need is the repeat until loop. And we want to repeat until our error is less than or equal to 2 degrees. So less than or equal to. And let's take an error from here. So, absolute value. Here. So until the absolute value of error is less than 2 or equal to 2. Command C. What's that one? There we go. Okay, cool. And now the first thing we need to do in our loop is to calculate the error. So set error to target angle minus the current angle, which is our yaw angle. So target angle minus yaw angle. And then we calculate the speed using the proportional algorithm. Do we have speed? Yes, we have speed. And if you need to make a variable called speed, then please go ahead. I already had a variable called speed defined here, but you may need to make a new variable called speed. So the proportional algorithm will be error times 0.5. And again, please make sure to tune your individual proportionality constant for your specific robot. Okay, and then after this, we have to do the lower bound clamp. So for that, we need a conditional statement. And so if the error is between 0 and 5, then we set sorry, if the speed is between 0 and 5, then we set the speed to 5. That's the positive part of the clamp. So error greater than 0 and error less than 5. Then we set error to 5. Oh, sorry. Oh, my bad. Yes, yes. I keep messing this up. Sorry. Speed. Yeah, we should be using speed. Where is speed? Okay, yeah. We should be using speed for this. And then we can just copy and paste that same conditional. And now we check for the negative part of it. So if speed is greater than -5, but less than 0, then we set speed to -5. And now we are done calculating our speed. Now we can move the motors. So in the more movement section, we have this start moving at 50% block. And we just need to start one wheel moving at speed. Oh, sorry. Okay. Yeah, okay, we got a request to wait a bit, so I'm gonna pause after this start moving block. So we need to start moving at speed, and then the other wheel needs to be -1 times speed, so that the two wheels are moving in the opposite directions and the robot turns. Okay, and I'm gonna just pause here so that everyone can get this code. Oh, and we need to stop the motors as well. So drag a stop moving block and make sure that this stop moving block is outside of the repeat until loop, because you don't want your robot stopping every time it goes through that loop. So yeah, and this is the turn. So I'll leave this code up here so that everyone can finish writing it on their own, and then you can test it on your robot if you have one. All right, are there any questions about this code? Everyone's good? All right. I think since some of them are just finishing writing this, yeah. And once you guys begin testing it, if you have any problems with the code, please let us know, and we will be happy to help you.
I'm still actually on the first part because I'm working my way through the code.
So by the first part, do you mean the other my block, or?
No, I mean the repeat until.
Oh, okay, yeah, that's completely fine. I'm gonna just leave this code up here until everyone is finished with writing the code, so that's completely fine. Just continue working through this.
Okay.
Okay. It's in operators, and at the bottom of operators, you'll see abs of. Yeah, and I'll just take this one away.
So we had a question about what time would we have a snack break? So at 12:15, we're gonna have a snack break. So if you want to grab lunch or grab your snack, you can do that at 12:15.
Okay, and for those of you who are finished with this, if you want to use it, just drag out the block P control gyro turn. And if you want to turn right, it's going to be a positive angle. If you want to turn left, it's going to be a negative angle. So if I wanted to turn left by 90 degrees, I would add -90 as my target angle. Okay.
Yeah.
Is that better than my?
And if your robot is overshooting, you may want to try decreasing your proportionality constant.
Also, I don't see it slowing down.
Yeah, that may be because the proportionality constant is too high, so it's too sudden of a deceleration. Yeah.
So everyone, you may want to listen to this. If your turns are too fast and you're still seeing some overshooting,
Yeah, so if your turn is too fast and it's overshooting, you may want to decrease your proportionality constant to make it decelerate slower. And if your robot is undershooting, it's decelerating too slowly, then you may want to increase your proportionality constant. Did everyone get that?
I would suggest having slightly lower.
Yeah, I just have a quick question.
Yeah.
So where's the block that says like set speed to block?
It's in the variables section. So have you created a variable called speed?
Not yet.
Okay, so you'll first need to click make a variable and create your variable called speed. And then you should see here, drag this block and you should be able to click speed. Did that answer your question? Okay.
Never mind, don't.
Doesn't matter. Oh, yeah, you can find mine.
Okay.
So.
Yeah, if there are any other questions, please ask them. We'll be happy to help.
Okay, do it generally. Okay. And don't set it on above this time. Make it face the camera. Make it say cheese. Okay, ready? Yeah. Wait, Illy, I think you don't set it at 90. Like, set it at the challenge.
Wait, hang on, don't move it right now.
Not right now.
You should be able to check that. Yeah.
Okay, redo.
Just wanna-
Oh, I didn't. You know what? We didn't do it. There's no.
I got you with the, so trying to get it on a, like a 90.
No, you might want to use it on the edge.
Oh, there we go.
Oh. No, I don't want this.
Oh,
Sorry. Sorry.
It's like 1.3.
No, threes.
I'm finishing up.
Okay, that's fine.
We're making it the field of a CMS. Or is it true?
Wait, does anyone know how to make comments in Spark? It should be within 2 degrees. That's the range of tolerance. Okay, that's good, but ideally you want to tune the proportionality constant until you're within your range of tolerance, which in this case is 2 degrees.
I can't see the screen.
You can't see the screen. Can you see it now? Okay.
I have a question.
Yep. Go ahead.
So all this is supposed to do is make sure that we aren't it's not going to go exactly at 90 degrees, but going two more than
Well,
two less or two more than 90.
well, I mean, ideally, we're aiming for as close to exactly 90 degrees as possible. But the reason we're allowing for the 2 degrees error is because if we wanted it to go exactly 90 degrees, we would have the problem of hunting, right? The robot would have to constantly go back and forth, searching for that exact 90 degrees. So to avoid that problem, we have a range of tolerance of 2 degrees. Does that answer your question?
Yeah, thank you.
Okay. Yep, no problem.
I'm ready.
You're ready? Okay. If you have a robot which you can test this on, go ahead and test it. Otherwise, that's fine. One thing about testing is again, please make sure to tune your proportionality constant depending on what you get. So if your robot is overshooting its angle, then you need to reduce your proportionality constant. And if your robot is undershooting its angle, you need to increase the proportionality constant. All right.
It's totally down.
Yeah.
What's the time? For anyone online, if you have completed this code and you've tested it, if you can, then you can go ahead and take a small break until we continue back for our next section.
So about 15 minutes.
Yeah. Yeah, I would say that, yeah. But the official break is at 12:15, so just don't go too far from your computer until then.
I know. How do you make those like captions?
Yes, so you have to right click on your program and then you can see add comment, and if you click add comment, then you can type whatever you want in this
Yeah,
box.
so do double tap like on iPad because I'm coding on my iPad.
Oh,
You would use 2 fingers or you could hold. So you could hold with double fingers on iPad?
I'm actually not sure. I've never used Spike Prime on an iPad before.
Both will work.
Okay. Oh, okay. How to add, well, how to add a comment on an iPad. He's coding on an iPad. Like,
Oh, comments.
yeah.
That's something that I normally do, but
Okay.
I think if you double click on the normal computer,
Right.
just double,
Yeah.
like,
have to
Maybe they
single
can-
out that block.
Maybe they can press and hold or see.
Yeah. Okay,
I'm surprised. So are all these blocks available on iPad? Which is why they said you have a computer, not an iPad.
I think as long as you have the version 3 of Spike Prime, it should be okay. Yeah,
So they are.
I-
Let me ask whoever's using
Um,
iPad, if they
I
could
think
see all the
Nikhil.
more motors.
I found out.
Yeah, so on the iPad, were you able to see all these blocks, or were there a few blocks which you couldn't see? Oh, thumbs up. Okay, cool. That's good to know. Let's see.
And that's all I do is I need to go to the Wi-Fi. Right, the Wi-Fi? Yeah, I know what it is. I know what it is. No, random topics, so, what?
So all the in-person students, you guys can reintroduce yourselves so that everyone remembers the names.
Lisa.
R-E-A-R.
Hi.
You said,
Hello, did you have a question?
No.
Okay.
on there, write it and let it work.
Okay, did everyone online have a chance to finish this program and test it if you have a robot available?
Yeah.
Cool, okay. Yeah, if there are any questions, please ask them. We'll be happy to help. And for everyone, both in person and online, who has a robot available, please make sure you do take this time to tune your proportionality constant, because that's going to be useful all along the season. The proportionality constant.
Oh, yeah.
Yeah.
You can
Okay,
fine-tune that so it works for iPad.
Sahasra, I see a message from you. It did not work. What exactly happened with your robot?
Nothing happened.
Nothing happened. Okay. Would you mind sharing your screen so I can take a look at your code?
Okay.
All right. Let me stop sharing. Nice. Okay. How do you max myself? There. Okay.
Oh, yes.
Okay. Can you? Okay. Cool. So, are A and B your movement motors?
Yes, they
Oh,
are.
okay.
movement.
So you see where you say set error to target angle? For that, you need to drag the input, the red target angle at the top. That's what you need to drag there. No.
This,
You see, define P control and gyro turn.
yeah.
So you see, yeah, yes.
Oh, okay.
So that's the input. And the same thing, you have set error to target angle minus yaw angle, the same thing there.
Okay.
Yeah, so what that does essentially is, so instead of using, oh, I think you replace the whole thing.
Is there Control Z?
Yeah, just drag that. Yeah, just,
he's sharing the screen.
yeah, yeah, that should work. Yep. No, oh, the previous one was what you want. So just replace that, yes. Cool, yeah. And the reason we do this is you want to make sure you're using the input on your my block for the target angle, not some
Okay.
variable that you created. But other
Okay.
than that, I think it looks good. Yeah.
Recording in progress.
Okay.
All right. Okay. Yeah, just let us know if it works again.
And,
Okay.
Mohita, I think we just saw you and let you back in. Please let us know if you missed any of the last few minutes.
It's okay. I'm actually sitting right next to Sahasra, so.
Okay, cool. Yeah, I just put my screen up again for anyone that needs this code or the information. Did everyone in person get their proportionality constant tuned and it worked for them?
Proportionality constant, can you show me
It's
what it
this
is?
one, the times 0.5, so
Yeah.
that needs to be tuned. It-
Like, depending on your robot?
Right, so if it's overshooting, then you need to reduce it. If it's undershooting, then you need to increase it.
No, it's been doing good.
It's been doing good,
Yeah,
cool.
so like the only difference is like by 1 or 2 degrees.
Okay, good, yeah. As long as you're within the range of tolerance, which here is 2 degrees, you should be good to go. All right,
How you driving the day? How do you drive in the day? I don't. No, I'm not talking to you. I'm totally
That's a lot of code.
yeah, this is a full P-control algorithm, so it's gonna be quite a bit of code, but this is, the good thing about this is because it's in a my block, you can just use it whenever you want by just using this one block right here. That's the good thing about my blocks.
Yeah.
We tried it and it still didn't work.
Okay, do you mind sharing your screen again? So what was the
Okay.
problem? Is it the same problem? It's just not moving at all?
Yeah, it kind of responds, but doesn't do anything.
Your voice is echoing, but I'll try muting myself. Do you mind saying that once more?
So it sort of responds, but it doesn't do anything. You know that sound? Actually, let me see if I can play. It just makes that sound and then it doesn't do anything.
Okay. Yeah, so are your movement motors A and B, is that correct?
I think it might be B and D.
Okay, a way to check that is by you can use your hand to rotate the wheels and then see which motors rotation sensor reading changes. Do you know how to do that?
Oh yeah, ask her to share screen and.
Can you still hear me?
Yeah, I can hear you.
Okay, yeah, I was asking, do you know how to use the rotation sensor readings to check which which motors are your drive motors?
Yeah.
Okay, so why don't you do that then and just confirm what your drive motors are?
Okay.
All right, and then let us
Okay, our drive motors are B and D.
B and D. Okay, so do you know which one is your right and which one is your left wheel?
No.
No, okay, so why don't you use the rotation sensors to figure that out and then make sure that when you set the movement motors, the right wheel is first.
Okay.
Okay, sounds good.
B is right and D is left.
Okay, so in this set movement motors block, just do B and D and make sure it's B plus D and not D plus B. All right.
Okay,
Okay, yeah, and if you,
so I should make it B plus D and not D plus B.
yes, correct. You
I
should,
already have it set like that.
oh, it was already like that in the first place?
Mhm.
Yeah, okay, why don't you try your program once more and then let us know what happens?
Okay.
Yeah. Okay. Oh, okay. Let us try that once more. I'll change this back. to A. Okay.
It still doesn't work.
Still doesn't work. Okay, do you mind sharing your screen so we can have another look at your program?
Okay.
All right.
How do I share again?
Where are you? It's my role.
Oh. That one. Okay, let's check. Set yaw angle to 0, set. Oh, your when program starts, you need to have a block attached to it. Okay, scroll up.
Mm-hmm. Oh, wait, 1 sec.
Yeah, oh, you can just press Control Z. Oh, okay, yeah. Good. Yeah, so do you see that yellow block?
Uh-huh.
Program starts. So, when you click run, only the code which is under that will get executed. So, go to your my blocks. On the side, yeah. So you see P control gyro turn.
Mm-hmm.
Yeah, so just attach that. No. Control Z. No. Yeah, drag that and attach it to your when program starts. Right, so when you click the run button, the only code that's gonna run is the code that's under the when program starts. So,
Okay.
right, so say you wanted to turn 90 degrees to the left, what would you put there? To the left though.
Oh, okay.
So what would you put there? Exactly. That's perfect. Okay, so now when you start your program, that block should execute and you should be able to turn your robot 90 degrees to the left. Okay,
Okay.
try that and let us know if it works.
Okay, works.
All right,
Thank you.
no problem. Glad that it worked for you. How do you do this? Okay, is everyone else completed this? Yes, okay. And I know some of you don't have a robot, which is fine, just you can encode this and test it on your own. That's completely fine.
We will
Okay,
be sharing all the slides.
yes,
Also the programs that they want, so. you
Yeah.
have access.
yeah, if you aren't able to hear that, we will be sharing all of the programs and all of the slides from the presentation. So you can always refer back to them on your own if you need them. Okay, so I believe everyone has completed this P control gyro turn. Okay. I'll go back to the slides then if no one needs this code and we can, oh, it's 12:11. Should we have our break now?
The left one, was that?
Well, this works for both. This works for both.
Yeah.
Just skip the, skip the one.
Yeah, so we can, or do we want to move on or have our
Let's
break?
go to that slide and let's leave it at that.
Okay.
And this slide and lunch break or slightly
Okay, so we're having a 15-minute.
15 minutes.
Okay, so we're now gonna have a 15-minute snack break or lunch break. So you can please come back at 12:30. Okay, a little bit longer than 15 minutes. So please come back at 12:30 and we will continue with PID drive straight. Send a message to everyone. Okay, yep. So see everyone back at 12:30 then. And thank you.
Give me a thought. Their computers.
Yeah,
Ed.
can everyone give a thumbs up?
Yeah,
if
give
you're
a thumbs up if you're
computer?
back. Yeah.
I'm back. I'm gonna
I
give you
know
a
you
thumbs
look
up.
back.
Sahasra, Mohita, Alex, and I think one more person at the end.
There.
Yeah.
Alex, but yeah, just Alex.
Just checking to make sure you're all back before we resume.
Yeah. Let's get that. Okay. Yeah, just give a thumbs up when you're back at your screen.
Can you send a message in chat? Please give a thumbs up once you're back.
Let's get thumbs up.
You lost the view.
I know. I'm just too lazy. Can you edit? You said it's a 15-minute break, right? Has it been 15 minutes?
Okay, yeah, it's been 17 minutes, so. Sahasra, Mohita, and Alex, I'm not sure if you're back. But we'd like to go ahead and get started so that there's
Yeah.
enough time. But please give a thumbs up if you're back.
Oh. All right, I think we'll probably just get started. Okay, Alex, you're back. Okay. That's good.
Mohita and Sahasra. Let's give them one more minute.
Yeah, okay, we'll give them one more minute to get back and then we'll start.
Issa, better not be playing games.
What?
You better not be playing games.
I can't hear you.
All right, let's refrain from conversations.
We're not.
Yeah.
Yeah, they do. See, even the FRC 9023 future Martians. I do.
Yeah, I think that's good.
Okay, yeah, let's go ahead and get started.
Ugh.
Okay, so we're just gonna go ahead and get started now. So, okay, so this is, we talked about turning with a gyro sensor. So now this is driving straight with a gyro sensor. Yeah, and one very important thing we're gonna be using is something called the PID algorithm, which we'll talk about next slide. Okay, so the PID algorithm, it is an algorithm that's used to accurately control mechanisms, and it's made of 3 parts: proportional, integral, and derivative. So that's why it's called PID. So proportional uses the current error to make a correction. So this is what we use in our gyro turn earlier.
where we had our error, and then based on that, we would turn at a certain speed. So when the error decreased, our speed also decreased. So integral uses the sum of all the previous errors and uses that to make a correction. And this can help a lot if your system is like making a mistake in only one direction. So that's what integral is. And then derivative makes a correction based on how fast your error is changing. So this can help smoothen out your corrections because it acts like a brake. So an easy way to think of the PID algorithm is, let's say you're riding a bike and you want to stay in a straight line. So if you move, let's say you move to the side of the line, then how much you're off the line by, then it's going to make a correction for that. So that's what proportional is. Like basically how far away from you are from the line, you're going to move back that much. And then integral is, let's say you keep like drifting off to one side of the line, the integral is going to like keep adding up all your errors. So it's going to know that you keep drifting off to one side. So it'll help you like basically always stay a little bit to the other side so that you stay on the line. And then derivative is, let's say you're like, derivative basically measures how fast you're moving away from the line and then uses that to make a correction. So it'll bring you back to the line. Does anyone have any questions about that?
So the PID algorithm is something that is used in many different ways. It's not just for software. It's not just for robotic software. It's used in chemical processes. It's used in industry in various ways. And it's called a feedback loop, wherein you're getting information, and based on that information, you're making a correction. And then after making the correction, you're checking again to see if there's an error. If there is, you're again sending some corrective information. So it's a feedback which will keep continuously going. One more example that I like to give, and all the students in Future Martians also kind of started with similar examples, was when you're trying to heat up iron and make things out of iron, the furnace has to keep that iron molten and maintain it in a particular range of temperature. If it becomes too, if it's not hot enough, then you cannot make anything because it's going to stop being flexible enough for you to tape it. But if you make it too hot, then it's going to have other issues with the metal. So let's say you need to maintain it between a certain range, and you all do similar stuff at home. We're all comfortable with a certain temperature at home, right? If it gets too cold, you start getting uncomfortable, or if it gets too hot, you get uncomfortable. So you're maintaining it within that range. And in those, the input is being given by you. Or maybe you have an automated system, and that's what the automated system is doing. It's constantly measuring. When the temperature falls below, it's going to start the heater up so that it gets warmer. Or if it gets too hot and goes beyond your upper range, then it is turn the air conditioner on to bring the temperature down. But those are basically inputs being given after measurements are being made so that you stay in the desired range. And that's exactly what's being done here with the PID algorithm.
Yeah. Okay, so now with that, if there's no questions, we can move on to how we can actually use this. Oh yeah, I see there's a question. What time does the meeting end? So
okay, so originally the meeting was supposed to end at 1 o'clock, but as you all know, we started about half an hour late. So we would like to end at 1:30. We'll try and wrap up by 1:15, but if possible, please plan on staying till 1:30.
okay. All right, so now we'll move on to the next slide. Yeah, okay. So this is a P control, like gyro driving straight. So we just talked about the PID algorithm. So this program doesn't use the full PID, it only uses the proportional part. So, and a big reason for this is in FLL, like integral and derivative are generally not needed. But one reason you might want like integral is if you have like a bad motor on one side, so your robot keeps drifting off that way. Integral would help fix that. Yeah, but okay, so this is the proportional part. Yeah, so the way this program works is there's two inputs. There's a speed and degrees input. So speed is this drive speed that you want to go at. So that's anywhere from 0 to 100%. And then your degrees are how far you want to move. So if you know how the motor's rotational sensor works, it basically 1 degree or one rotation of the motor is 360 degrees. So if you input like, let's say 1080 degrees, then your wheel is gonna spin 3 times. So that's what that means.
Oh, no,
Yeah.
you look at centimeters or degrees?
Degrees. Yeah. Yeah, and then, okay, so all right, let's start with the actual like program now. So the first 2 blocks set relative position to 0. So what that does is it sets the motor's rotational sensors like to be 0 degrees. So it basically just resets it. And then it waits for 0.5 seconds. Yeah. Oh yeah, so for the my block. Oh, here, we'll get into coding it like after I just quickly go through the actual thing. Yeah.
So you can listen for the
Yeah.
logic. Right?
All right, so the next step is it sets the yaw angle to 0. So that's just to reset the gyro sensor. And then we set movement motors, we set it to brake, and then we set movement speed to speed. So what that does is like whatever speed you input when you use the block, it sets your movement speed to that. And then now we also have a couple variables here. We have target, KP. So if you remember from our gyro turn, we had our like proportional constant. So that's the same thing. That's what KP is. It's the constant that you multiply to your error for for proportional. Yeah. And then we also set our average degrees to 0. That's another variable. And average degrees. Yeah, and so what average degrees is, it's basically because we have 2 drive motors, when we're like seeing how far we want to move, like when we said we wanted to move like 1080 degrees, to have our like to track that, we just take the average of the 2 drive motors rotational sensors, and that makes sure that it's tracking like the whole robot and not just like one side. Yeah. Okay, so then we have this repeat until loop, and the repeat until is basically it's taking average degrees, which is basically how far the robot has already moved, and then it's checking if it's equal to the target amount of degrees or if it's greater than that. So basically it's checking if average degrees is greater than or equal to the target degrees, and then if it is, it would finish the program and stop moving. So now inside the repeat until loop, we set average degrees. That's the first thing we do. And that's just to make sure that every time we go through the loop, it updates that value so we know how far the robot has moved. And the second thing we do is you set error to target minus the current yaw angle. So that's really similar to the gyro turn. And this is our proportional part. So the target would be 0 because when we reset our yaw angle to 0, that means that like 0 degrees means our robot is pointing straight. And our target is for the robot to move straight. So that's why target is 0. So we set the error to target minus the current yaw angle. So what that means is, let's say we're like to the right by 2 degrees, then our error would be -2. So we know we need to move 2 degrees to the left in order to fix that error. And then now we have a start moving block, and has error times KP. So if you remember earlier, we set our KP to 0.8, and then our error is whatever is calculated before. Yeah. All right, so now, is there any questions so far?
Yeah, please don't hesitate to ask questions. If this is the first time you're dealing with the PID algorithm, I'm sure there's going to be clarifications that you might want to get. So please don't hesitate. Any questions, we'll be happy to answer. So using the gyro-based currents, proportional currents, and using the proportional going state, this is exactly how teams are able to make their robots way more precise. So every run you get it to work. And if there's slipping or if there's something that's happening that was not expected, you're still able to overcome that by using these algorithms. So that's why we ask that you try and understand this completely. and then you'll be able to leverage what you built here in your competition.
Okay. So if there's no questions, we can move on to the actual coding. So let me switch my screen.
If you have a copy, I suggest just rebuild that once again on the side. Next mission for this stuff.
Oh, yeah, that's what I'm gonna do. Okay. Let's see. Alright, so, okay. So the first step, is everybody ready to like code it? Oh, yeah. Yeah. Is this good? Yeah. Okay, so the first step is we need to make a my block. So we can just call this like, yeah, you call it P control gyro straight. Okay, and so once you have that, then you're gonna want to add an input. So our first input is gonna be our speed. And then you can add a text and like label that if you want to make it easier. And then add a second input, and that's gonna be degrees. So that's how many degrees you want like the wheels to rotate. And you just add a text to label that. Okay, so once everybody has this typed out, just like just give a thumbs up. And also, if you need help with anything at any point, just you can just unmute and ask a question. Or you can also raise your hand and I can call on you. So in person, do you guys all have like this my block typed up? Okay.
Can you show us how to make the block again?
Oh yeah, here, let me I can show you again really quick. So let me just start from scratch. So click make a block. And then so we're gonna name the block P control gyro straight. And then what you do next is add an input and then call this speed. And once you added the input, then add a label and just do speed again. The reason why we add this label is so that when you're actually using the block, you know like which input is speed and which input is degrees.
Okay.
Easier. Yeah, so then once you have your speed
But
label,
I clicked add an input. Actually, never mind.
okay. All right, and then after you do your speed label, add another input and call this degrees, and then add a label for that and call it degrees. All right. Yeah. Were you able to get that? The microphone is going through here. Yeah, it should. That's what I have it selected as. Yeah. In person, has everybody completed this step? Okay. Almost again. So online, does everybody have this?
Yes, did you say you needed a moment? You have it.
Okay, you have, okay. All right, I think everybody has it, so I'm gonna save. Okay, so now we have define. So the first step is go to your more motors. So remember we added those extensions earlier. So we're gonna want the more motors extension. And you want to drag out this block. You want to drag out 2 of them. And so whatever your movement motors are, so like for example, my movement motors are A plus E. So you want to set the first one to like one of them. So we have the first one set to A. and on my second one set to E. So you're gonna want to do that. Set these two to whatever your movement motors are. In person, does everybody have this step done? Okay. All right, so then the next step is here. Go to sensors and drag out the set yaw angle to 0. Is this wait what is on this? Okay. Yeah, so set your yaw angle to 0. And then after that, just run the normal like set movement motors. I'm just gonna duplicate it. Yeah, so you're gonna want to set your movement motors to A plus E and set your movement motors to brake at stop. And then drag out a set movement speed. And then what we're gonna put here is you drag speed down and then just put that in there. The third movement. Oh, so the third one is a set movement speed. So drag out your set movement speed and then drag down the speed from up here and put it in there. Yeah. Does anyone online need help with any of these steps?
Question, is that all?
Yeah, so far that's all. Yeah, we still have all of this stuff to get through.
Oh,
Okay. All right, is everybody at this step?
yeah.
Okay, I'm gonna start moving on then. So now we're gonna need to create a few variables. So create a variable. Here, let me try just a second. Okay, so you guys are gonna want to create a variable target. So create target, and then you want to create a KP, and then you want to create an average degrees. So yeah, so once everybody has these 3 variables created, just let me know. And also you can set your KP to 0.8. But one thing is this value, the KP value, will be different on every robot. So just use 0.8 as like a starting value, and then you'll kind of have to tune it like as you go for your robot.
It's like a lot of code.
So sorry, what was that a question?
No.
Okay. Does anyone in person have questions or they all? Yeah, so online you can just give me a thumbs up when you're at this step. Yeah. Okay. Vito's here. Then okay, Alex is here. Then Nikhil and Millen, are you guys here?
Yeah, I'm here.
Okay.
Yeah, I'm here.
All right, great. Then in that case, we'll move on. So now we're gonna want to go to control and drag out a repeat until. And then we want to drag out. Okay. So drag out an or. Where is it? Yeah, drag out an or, drag out an equal to, and then okay, and then drag out a greater than. So put the equal to in here and the or in there. And then now go to your variables and drag out average degrees and put them in those ones. Yeah. So yeah, put your average degrees in here and here. And then once you've done that, drag out the degrees from up there and then put it in here and here. And once you're done with all of that, you can drag this and put it in there. And so basically now what this is doing is it's basically saying we're gonna keep moving until our current, like our average degrees, so how many degrees we've already gone equals our target degrees, and then or if it's greater than, and then we're gonna stop. Yeah. Okay, does everybody in person have this done? Yeah. Here, let me zoom in a bit. And does anyone online need help or have any questions?
I have one. So for the code, why would you put 0.8 for the KP?
Oh, okay. So the KP, it's that's our proportional constant. So it may not make a ton of sense right now, but later on, I'll get into that later on. But just think of it as like kind of basically determines like how quickly your robot like makes a correction. Yeah, think of it like that. So 0.8 is like a good starting value. And then you can, if you want your robot to kind of make slower corrections, like if your robot is kind of like when it's moving, if it's really jerky, like it's just going back and forth, then you could lower this value and that would help with that. Yeah. But we'll get a bit more into that later. Okay, does everybody have this green bit done? Okay. And online, okay. All right, great. So we'll move on to the what's inside the conditional. So the first thing is we want to set average degrees to, is that, yeah, okay, let me just, actually, I'll just make it, okay. We want to set our average degrees to, so drag out an operator. So you want a divided by, and you want an addition. So put your addition in there, and then put 2 over here. And then go to your more motors bit and drag out like this relative position. Drag out 2 of them. So again, this has to be like your 2 movement motors. So my movement motors are A and E. So I'm gonna make this A, and then this is gonna be E. So what this is basically doing is it's finding the average of our 2 like sensor inputs from each motor. Yeah. So okay, and then once you have that, just actually, I actually forgot one step. So because we have the 2 motors, like our 2 drive motors are in opposite directions, one of the motors, like the sensor input, is going to be negative. So you want to make sure you multiply by -1. So for example, so like when the robot's moving forward, the E motor is gonna like give a positive reading for the degrees, but the A motor is gonna give a negative reading because the motor is spinning the other way. So you need to multiply it by -1 to counteract that, and then yeah, put it in there. Yeah. And then once you have this bit, you can set your average degrees to that. So does anyone online have any questions?
In person, everyone.
Does everyone in person have this bit of code done?
Yeah,
Yeah, okay. Online, is anyone still working on this part? Okay, it sounds like everybody's done, so I'm gonna move on to the next part. So the next part is our calculating our error. So for that, we are going to drag that out. So set error to where is it? Sorry, so we need to get a minus. So set error to target angle. So that is, yes, target. So set error to target minus the current yaw angle. So target minus yaw angle. Yeah. Okay. And then after that, we want to drag out. So, all right. So after this one, go to your movement and then drag out and start moving. Yeah, this one. So basically it should say start moving, and then it should be the one where you can give like a number value between -100 and +100. So drag that one out. This says start moving, and it should say like right 30, I think. Like, yeah, this one here. And then once you've gotten this, then you can actually input your proportional correction. So you drag out a multiplication block, and you want to multiply error times KP. So basically what you can see here is we calculated our error, and then we're inputting it into like our start moving, but we're multiplying it by KP. So what that means is if KP is like a lower value, it's going to kind of like minimize this whole overall thing, which means our corrections are going to be like less aggressive. But if KP is higher, then it's going to increase the error. So it's going to make the corrections even more aggressive. Yeah.
So let's focus on the logic being out here. That's code itself, you guys can easily copy. So I really want you guys to listen to what's being told so that it makes sense.
Does anyone have any questions about that?
What does KP stand for?
It doesn't really stand for. It's like, oh, it stands for proportionality constant. Yeah. Okay. So, oh yeah, and then the last step, pretty easy. Just drag out a stop moving and put that at the end there. Okay, and then that should be everything, I think. Yeah, that should be everything. Okay. Yeah, we can test it now.
So just, yeah, while the testing is going on, just to simplify what this program is really doing, right? Think of it as I'm a human being who's walking in a straight line. Okay. But I've blindfolded myself, so I don't know if I'm going straight. And then my friends are helping me walk straight on that line. As I'm going, I keep asking, am I still straight? And then my friend says, no, you're moving a little to the left. And then, well, let's have a better way of saying little to the left. Maybe they say, yeah, you look like you're 5 degrees to the left or something like that. And then that gives me an idea of how much to change my direction as I continue walking. So I kind of take a small step to the right and then continue. So that taking that small step to the right, that's what the whole multiplication of the error and KP is. How aggressively I'm correcting myself is decided by KP. And how much I really have to correct myself, error is going to tell me that. Yes.
So in the code you set to greater number or more aggressively correct itself?
It might even end up making a mistake. So it's like when I'm walking left, if I go 10 degrees to the left, but then if my KP is 5 times, when I correct myself, I'm gonna end up all the way to the right, right? And we don't want that. We want to correct ourselves just enough to get back to being straight. That's why that correction factor is, it's almost always going to be 1 or less, but there may be some situations where it's a little bit more than 1. Guys, you have to correct me if
We
that's.
can actually show you what happens if you put your KP value too high.
But anyway, just to complete this simplification. So as my friends tell me to correct myself, I correct myself and keep going straight. That's the whole idea. And your friends here are the sensor and the corrective input you're giving.
Okay, so this is what happens if you put your KP value too high. So just look at that robot over there. You see if I give it a bit of, you know, but okay, you can kind of see how it's moving around like a bunch. You don't want it to like move around too much. You want it to only move around as much as it has to in order to correct itself. Let me
So what's happening here is it's over.
What if you hit it? Will it still go straight?
yeah, I can actually show you that. Yeah, it will go straight. So
But you want to use a better KP like this.
this is like, yeah, okay, so this is with a really high KP value. You can see it's just stuck. It's basically just. Yeah, it is with a really high KP value. It's just stuck. It's not able to actually move. So yeah. So let me change it to like good value. So wait, can you request it? So now I can hit it and show you guys how it's correct. Oh yeah. Did you guys want to test like the power level? No, I don't. Yeah, those are correct. Yeah. So this isn't necessarily for rotations, it's degrees. So one rotation is 360 degrees. So if you want to move your rotations, so or you can those guys. So now, yeah. Yeah, I'm gonna put you this. Here, you can increase your like degrees and then you can go over. Yeah. Oh yeah, you need to be pretty. Oh yeah, he's so one person who doesn't have one.
Okay, are we ready? Yeah. Okay. I'm gonna put country number, random number, 256.
Ellie!
Yeah, you can take some screen. I'd say I put this one at like 3,000 and it got like from here to like.
Or maybe go 1,500.
Yeah, this should be safe.
Okay, ready? Okay, 3, 2, 1. I'll go down slow since.
What did you, how many did you go before that? Oh, so I'm gonna hit it and you just.
Oh, wow. Guys, I'm gonna check it.
See this?
Do a light blue. Do a light blue. Do it again. Oh wow, it just rapidly.
Right, that's something that joy to everyone, right? When you see a robot fixing itself.
Wait, on the computer I did. Why is this not working? Wait, I got it.
Oh, there you got it. It's on, it's set to. No, this one on this.
I'm sure, actually.
Oh, this, yeah. Oh, yeah.
Tell me like really straight. What are you doing?
So to all the attendees who are online, are you getting a chance to run this code on your robots if you have a robot?
I'm watching mine run.
Sorry, Milan, did you said something too?
Mine is right in front of the camera.
Right, yeah. Sahasra, Mohita, and Alex, have you guys had a chance to
Knock it.
run this yet? Okay, that's good.
Yeah, we tried it.
Okay, that's awesome.
Oh.
Is this the end of the class?
Oh, no, not yet.
Not too much of an aggressive buff.
I don't think.
Not too.
You can show and indicate.
Yeah, like push. Not too much. Like,
I can hold
yeah.
that for you.
3, 2, 1. Now let's just test the aggressiveness of buff. I gotta get him. Wait, no, we can just yeah, we can do this. No. What?
So do you want to raise them? Do you want to? Or?
Well, I mean, it's get that aggressive.
It's not bad.
Yeah.
Yeah, we really like that. Alright.
No, the video was not stopped. Whatever you're doing was like.
I know. It's not that.
Imagine making an FLL.
Wait, good idea. That advanced driving is good.
Good job, Trent.
Do it again.
It's gonna run into your robot.
Here, we don't care.
What are you guys doing?
It's not gonna put it down.
Okay, not gonna play battle box.
Come on, guys, be serious.
Ari, did you get?
No, he got it. Yeah. Okay, oh, wait, should we move on? Wait, should we move on now? Okay, we're gonna move on. So this program was only using the proportional part of PID. So we're gonna move on to a program that uses the full PID. So yeah, so if everybody could get back to your seats, and then online, if everybody could get ready to listen to this one more slide. Here, we'll get there.
That's fine.
Okay, so just give a thumbs up if you're back and ready. Yeah, I think everyone online is good. Alex, you're good. Okay, I
can't
think
see the screen.
you can't, oh, you can't see the screen? Or are you able to see like the PID gyro straight slide?
I can see it, but it's very small and I can't zoom in.
Or you can,
Oh.
so the code will be shown in a zoomed in.
Are you talking, no, you're just talking about like,
I think it's from the code. Yeah, you can.
okay.
you can-
Here, we'll zoom in later and it'll be a bit easier to see. Okay, so we're gonna get started now. So this program here uses the full PID algorithm. So what that means is we have a couple of new variables. We have the,
Lisa and English, we are going to discuss this because we're explaining the full PID how that works.
so we have a couple of new variables. We have integral, derivative, last error, KI, and KD. So KI and KD are pretty simple. They're the exact same thing as KP, except they're for the integral and derivative part. And so the easiest way to do this is to, let's take a look at the repeat until. So if you notice, this program is really similar to the one we just did, but there are a couple minor differences. So earlier we had just the set error, like to target minus yaw angle, but now we have two more lines after that. We have change integral by error and set derivative to error minus last error. So we'll start the integral part. So what this does is every time you go through this loop, it's adding the current error onto the integral. And the reason like why we do this is because integral is the sum of all of your previous errors. So that's exactly what this is doing. It's integral is a variable that basically just has the sum of all the errors. So yeah, that's the integral part. And then derivative is error minus last error. And this is derivative because that shows how quickly your error changed. Because let's say your previous error was -1, but then now your current error is -3. Then now you know that your error changed by like 2. So that's what derivative is. And
So just want to add a couple of things here. Now, the integral, the best way to understand what correcting the using the integral part does is, now if your robot for some reason is going on tending to turn one way all the time, then if you see that error for integral is going to keep adding up. And so what will happen is whenever corrections are applied, it will remember, hey, this robot keeps tending to go to the left. So let me add a little more extra correction towards the right so that it comes back on path. Otherwise, what's going to happen is if you just keep giving only proportional corrections, you might end up in a path that is straight, but parallel to your intended path. Now, like we've seen, most FLL robots, you will not need IND because that doesn't typically happen. But like was mentioned, if you happen to have one motor which is weak or starting to go bad, then this will help. You know, let's say it's happening right in the middle of your competition. Having the eye could help you come back to the right path. So instead of ending up parallel to your intended path, you will stay on your straight line. That's where the integral comes into play. So if your errors are, oh, once it's left side, another time it's right side, they're going to cancel out. So that overall integral value, because it's like a bucket where you're going on putting your errors. Once it might be a positive error, another time it might be a negative error. And when it's positive and negative, they cancel out and it will remain a very small value. So because you don't need that much extra correction. But if it's always tending to go to the left, then that integral value will keep increasing, which means it knows that your robot for some reason is going on, tracking more and more to the left. So it will start adding a higher correction to go back to the right because it's a bucket holding all these corrections happening. And now for derivative, if you have an error which is happening very extremely, like all of a sudden, then by using that last error, you are anticipating what error might happen and you're giving it that extra correction. Again, this is even rarer for requirement because mostly if our motors are that bad, we'll probably end up changing those motors, not having to rely totally on software. But these are important to know because as has been mentioned, you will most probably use the P control in all your FLL code. but you need to know that PID includes integral and includes derivative. And you may use that, you may not use it in FLL, but you may use that in FTC or you may use that in FRC. So just knowing this is definitely important, which is why this is being covered as part of this stack.
Okay, yeah, so now the way we combine all of these is in our start moving block. So earlier we had just error times KP, but now what you do is you just add all three of them up, and that's gonna be the output of your PID controller. So that's gonna be the correction that you make when you're moving. And then at the end you have the stop moving block. So one thing is, because we're running a bit low on time, you guys aren't gonna code and test this, but what we can do is we can show you some demonstrations on our robot, just to show you like the effects of like integral and derivative. So I'm just gonna get some code ready really quick.
So while he's doing that, we would strongly suggest that when you are doing this for competition, start with the P control. Use that, the one which you all just coded and had working. Start by using that, and almost certainly that is all you will need. But if for some reason you want to go try the PID, the full PID, this code is available in the slideshow. We will be providing the code files, so you will have it available if you want to go ahead and try those values. But just remember, P is probably going to be a value, I'm sorry, KP is going to be a value just under 1, but KI should be a really small value. You don't want to have a very large KI. It's probably going to be something like 0.01 or 0.02, something of that nature. And then with B, I would say for KD, again, keep it a low value. Any suggestions, you guys, for KD, if they're going to try it? Right. So yeah, I would say put in some values. Start with maybe like 0.1 or less for KD. But the proportional, that's the important one, and that's the one you should make sure you tune correctly and for competition with the P control. And the KI and KD, you can play around and figure out those for you. And I would suggest start with KD 0, play around with KI. And once you have that working, then start trying to tune KD. Do not try to tune multiple things at once. It's hard to do it like that. So first nail your KP, then KI and KD if you want to. But like I said, most probably KP is all you need and proportional control is all you're going to need.
Yeah, also one quick thing, don't reprogram like other people's bricks, because it's not good, because then they won't know if it's theirs. Yes, because this one got renamed.
Oh,
Yeah. Okay, so all right, here we can demonstrate now. So as you can see, it corrects itself the same way as before, but now one of the so now I'll figure out integral rules. So let's say I hold it like one side for like a really long time. Now it's, you can see how it's, because it was on that side for so long, that correction was so figured. That's how it works. And for derivative, that's kind of like just if you smack it, that's derivative kind of helps smoothen out that correction by making it not too aggressive.
So if you got that, the correction, if it was too aggressive, it would have overcorrected.
Yeah, I was overcorrecting it.
And that's where the case. Okay, so any questions from anyone?
Some stuff in the chat. Oh, no, this is a 1-day camp, so there won't be anything tomorrow.
So yeah, the intention of this camp was to make sure that you have the ability to turn and go straight reliably. And we hope that what you've learned here and what you've coded will help you achieve that. We wish you all the best for your season. Looks like it's going to be an amazing season, right? And that innovation project, that is so fun. You have a lot of options on what you want to research and learn about. Okay, so, if there's anything you guys want to let us know, like right now, please feel free. Now's a good time. We'll call this the next few minutes as Q&A, or you can wave your goodbyes. Yeah. So we will send a form just to seek your feedback, to see if you enjoyed this, if you felt it was helpful, and if you felt that something else should have been thought or something done different. Okay. Good luck, everyone. Have a great season. You all want to wish them good luck too? Good luck.
Bye. Thank you.
Bye.
Bye, everyone.
Bye, sir.